Good evening, everyone, and welcome to Trig Identities part number 26. And what we're going to cover tonight is this. You see this little equation right here? This could give you a lot of trouble, and it gave me a lot of trouble too. And you sit there going, why would this give you a lot of trouble? Well, because if you see it in a different light, it can give you a lot of trouble real fast, okay? A lot of you people are used to, say, this type of equation. A equals 1, 8, 0 minus B. And then if you put this equal sign right here, you say, well, wait a minute. You can't just make that 180 degrees just disappear without a trace. And under normal circumstances, you would be correct. But we're not dealing with A and B and 180. Okay, we're dealing with tangent values. Now that is a completely different subject. Okay, the goal on something like this is to make sure, and I got this pair of scales to illustrate. I'm going to show this to you. So bear with me, folks. I know this is going to be kind of a lengthy video, but I do have to show you all this. Okay. Now, let me take this off here for just a second. This is a 10-gram weight, and this is a pair of scales. Now, there's already a 10-gram weight in this. Okay. Now, we're going to put this one in here. Now then, here's what I want you to do. Every time you see an equal sign, I want you to visualize this pole right here. See this pole right here? Okay? I want you to visualize this pole. Okay? And everything that's on the left must equal everything that's on the right. That's the way this has to work. Now, here's the thing. If we didn't put the word tangent up here, this wouldn't work. Okay, you can say, well, A does equal 180 degrees minus B. Okay, in this particular case, you would just say 180 minus B. This part right here would work. You can say something like that. But what you can't do is say that this is equal to this, which is equal to this. That would be the transitive property, saying, well, if A equals B and B equals C, then therefore A must also equal C. You can't say that A is equal to negative B because of this 180 degrees right here. But that's not what we're looking for. What we're looking for is tangent values. Now you say, well, where does tangent come from? It's not like sines and cosines, okay? It actually came from something called the Book of Shadows. And in Euclid's Elements, of course, he covered the tangent line in Euclid Book 3, but he didn't call it a tangent line. So you said you're flipping through Euclid Book 3, and you say, well, there is no tangent line. Actually, there was. He actually had a little circle like this, and a line that actually touched that circle, and that actually is a tangent line, but he didn't call it that. Now, Euclid did write a book of conics, but it got lost. That's a problem. So, there was another guy named Apollonius, and here's his book. And in Euclid, not Euclid, but in Apollonius, book 1, proposition number 17, he actually drew a figure much like this. It wasn't exactly like this, but it was much like this. And this line became a tangent line. That's what he called a tangent line. Now, you say, okay, well, here's the thing. You have the axis of this cone. He actually drew a cone, and there's the axis. And this line touches that axis at exactly one point. And he said any line that touches an axis like this at one singular point is called a tangent line. So if you draw it like this, you have your axis line, you have your tangent line, you have this line right here, which actually makes this into a right-angled triangle. Well, then you can start using the Pythagorean Theorem. And there you go. You got your sine, your cosine, and your tangent. Okay? And like I said, this came from the Book of Shadows. You can research Book of Shadows all you want, and if you want to leave some kind of a comment about Book of Shadows, you can go ahead and do so. You can leave some kind of a web address so we all can look about Book of Shadows, that kind of thing. Okay? And there's actually a thing called a gnomon, and it's sort of like an L. Okay? And it was all based on this gnomon and so on and so forth. There's a whole bunch of story behind that. I'm not going to get into it here. But anyway, what we're doing is we're not looking for A and B. We're looking for their tangent values. That's where the 180 comes from, okay? Now you say, well, wait a minute. 180 degrees. That's what all this is all about. Okay, so you're talking about a unit circle with 180 degrees. Now, let me show you something. Okay? Because once you begin to understand all of this, it makes a lot more sense than just presenting an equation like this. Because you present an equation like this and people are just like, what the thunder's going on here? But anyway, what we're going to do is we're going to draw something called a hexagon. Okay? And we're going to have a line that will come across here, somewhere like this, and a line that comes across here. You say, well, that's a well, you could call this a trapezoid, whatever you want to call it. But anyway, you're going to have triangles like this, and another triangle like that. And boy, that was a terrible drawing here. Let's try that again. Whole purpose. I'm doing so well here that I goof everything up. Anyway, now let's say okay. And this is not going to be exact, obviously. I'm not the best person to draw anything. Anyway, there's your basic hexagon, and of course there's a circle that kind of meets all these points. And that is one of the worst looking circles you're ever going to see. It's kind of deflated. Whatever. But anyway, there's a hexagon in a circle. You say, well, why does there have to be a hexagon in a circle? Well, of course, you have to keep in mind that all of these angles here are 60-degree angles. All of them. Now, if you have all these angles 60 degrees, that's going to make that an equal angular triangle. Well, if you have an equal angular triangle, you're also going to have an equilateral triangle. Now, in this particular case, this circle that we drew around the hexagon is a unit circle. That means that this is 1 inch. This is a 1 inch radius here. Now, if this is a 1 inch radius and we said all three sides are equal sides, well, this is going to be 1 inch here and 1 inch here. Okay? Now, we've already established by Apollonius Book 1, Proposition number 17, that one of these three sides is going to be a tangent line. So we drew the right angle triangle, we had the Pythagorean Theorem, boom, there you go. Alright, now you could also chop this angle up into a 30-degree angle, which of course would make this 90 degrees here, this would be 60, this would be 90, this would be 30, and of course then this would become a tangent line. Okay, because it would be the large, well actually this wouldn't be the, this would not be the tangent line, this would be. The longest line of the three would actually be the tangent line. But this is where all this stuff comes from. So if we're thinking of tangent values rather than just regular numbers, then this actually starts to work. Okay? Like I said, we're not finding A, we're finding the tangent of A. So what we do is we take A, which in this case would be 60 degrees, and we look up a chart. Okay? And we look up the tangent chart of 60 degrees, and we find whatever 60 degrees correlated with, and that's the value you're looking for. Okay? So what we're saying to you is that if A is over 90 degrees, what we're going to do is we're going to subtract the value of A from 180. Okay? But in this case, we're not going to really call it A, because what we're going to do is we're going to say that, remember, when you have an angle, like thus, okay? Now this is getting kind of complicated. Let's say that angle is 60 degrees, okay? Now, the thing is, from here all the way over here is 180 degrees. Now, what is 180 degrees minus 60? Well, of course, this side is 120 degrees. Okay. So, let's say we just reverse it. Now we have A like this, and it's 120. This is 60. Now, if you look at a chart of all the tangent values, you'll see that they go from 0 degrees to 90, and they don't go any farther than that. So, instead of finding the tangent value of 120 degrees, you're going to find the tangent value of 60. This is A here, this is B here. But the thing is that once you find the tangent value of B, you're going to make whatever value that is into negative. Because the negative value of tangent of B is equal to the tangent value of A. And that's how all this can actually work out. Remember, when you throw a ball up in the air, it's going to curve around and it's going to start coming back down. What goes up must come down. So that's where this comes from. So like I said, you're not trying to find the value of B. You're not trying to find 60 degrees. You're trying to find the tangent value of B, which is a completely different subject. And if you're trying to find the tangent value of B, once you've found it, you turn it into a negative, and it becomes the tangent value of A. Because this line does not change in length just because it's going to be the same length whether you call it A, which is 120 degrees, or B, which is 60. That line is going to stay the same length. It's not going to change length despite you doing 120 or 60. It's the same line. That's why. I know that's not a perfect explanation for all this, but you have seen Ptolemy's table of chords through that. You remember that hexagon I drew in that circle? That's where Ptolemy's table of chords came from. And by seeing this, and by seeing this, and by seeing all the things I've just shown you, and Apollonius Book 1, Proposition number 17, and Euclid Book 3, you kind of get an idea that you're not looking for the value of B, you're looking for the tangent value of B, which is a completely different subject. And that's how this can finally work. Now, I know that your brain is spinning right about that now, but those extra details will make this a lot more acceptable. Because, like I said, you're not trying to find the value of B, you're trying to find the tangent value of B and then turning that into a negative. And that actually is, when you all get it figured up and done, the same value as the tangent of A, and that's because this line doesn't change in its length or anything else, whether you get the tangent of A, which is 120 degrees, or the tangent of B, which is 60. That doesn't change length at all. Okay. So those are a lot of extra details and a lot of things you've never heard of before, and hopefully you'll get that into your mind as you're continuing on in your study of calculus. But anyway, I will cover this a little more in depth in Trig Identities Part 27 when we discuss the law of tangents, because there actually is a law of tangents and I do cover that as well. But that makes this equation a lot more palatable once you see that. Alright. I will tell you more in a future video, so I would like for you to stay tuned.